everybody. My name is Miguel Molero, and I'm going to present the anisotropy of protons and light primary nuclei measured with the Alpha Magnetic Spectrometer. So you, at this point, you probably already know all these things, but essentially, when a supernova remnant explodes, ejects material to the space, in particular primary cosmic rays, they travel through space, and at some point we measure them at the Earth. AMS is a detector on top of the ISS and has presented at the moment the most precise measurements of the proton and light primary nuclei, helium, carbon, and oxygen as a function of the rigidity. I show here in this plot on the left the flux of protons, and according to the traditional models, it was believed to be described by a simple power law, but it was shown that actually it has a break around 200 GeVs, which also was shown in the helium, carbon, and oxygen fluxes, as you can see here. These observations typically require the modification of cosmic ray transport models or the inclusion of nearby sources of high rigidity events. In this context, the measurement of the anisotropy of cosmic rays could be very important because like a nearby sources could induce some degree of anisotropy that we could measure. In this sense, the measurement of anisotropies provide a complementary characterization to the rigidity dependence of the fluxes that may help to understand these observations. So for those of you who came to my previous talk of anisotropies, these slides are very similar. So, and for those of you who didn't attend it, I will explain it once again. So in order to measure anisotropies, we first need to define a reference system where our signal can be measured. It's enhanced. For this purpose, we use galactic coordinates, which are defined with the center in the solar system. One of the directions, which is called the forward-backward direction, pointing to the galactic center, the north-south direction perpendicular to the galactic plane, and the east-west direction that completes this reference system. Once we have the reference system, we expand the flux of cosmic rays in two parts, one isotropic part and one anisotropic part, which depends on the multipolar components and the real basis of spherical harmonics. For this presentation, I will get to the dipole components, which are defined as the east-west, north-south, and forward-backward, and correspond to the multipolar components, A, 1 minus 1, 1 plus 0, and 1 plus 1. When we have all the dipole components, we can compute the dipole amplitude, which essentially provides you the degree of the anisotropy that you can measure. And you can compute it with the three dipole components and this formula. Another very important aspect for the measurement of anisotropies is to understand the exposure of AMS. AMS is on top of the ISS, which is orbiting the Earth from minus 52 degrees to plus 52 degrees. And as you can see in this plot, the ISS spends more time at high latitudes. If you take into account this effect, plus that the detector is tilted 12 degrees with respect to the zenith, and also that it has a field of view, this is the exposure that you get, where you can see that the northern hemisphere is much more exposed than the southern hemisphere. Finally, if we transform this exposure time to galactic coordinates, which is the reference system we are going to use to present our results, this is the exposure that you have. And of course, the map of events is going to have the same aspect. In particular, we are going to present results for 10 years of data taking. Once we have all these ingredients, we can compute the anisotropy. For that, we have to compare our map of events with a reference, which typically describes the response of the detector to an isotropic flux. And this is very important because the comparison of the map of events with our reference will give us our anisotropy. As an example, I show here the map of proton events for rigidities above 18 GeVs, where we have a total of 140 million events. And for the anisotropy analysis, we divide our sample in 9 cumulative rigidity ranges which go from 18 GeVs to 1 GeV. But in order to compute the anisotropies, we need to take into account the effect of the efficiencies into the reference map. For that, and as an example, I show here the most relevant efficiency, which is the trigger efficiency as a function of the magnetic latitude. And as you can see, at the highest latitudes, there is a drop of about 3% that in this particular case can be reduced by constraining our analysis to lower latitudes from minus 0.8 to 0.8, and this effect is reduced. So we have under control our systematics. But this is just the 1D plot. If we go to the 3D one, you see that these drops at high latitudes have an impact into the map of galactic coordinates that if we don't take into account in our reference map, it may pop up as spurious effects. That's why we have to take it into account. Once we have all this into account, we can compute the anisotropy, and what I show here are the three dipole components: east, west, north, south, and forward, backward, where the black dots correspond to the data points. The green and yellow lines correspond to the 1 sigma and 2 sigma error bands, and the solid line corresponds to the statistical plus systematic errors, and the dashed one to the just statistical ones. As you can see from here, all the data points are within 1 or 2 sigmas, so this is consistent with isotropy. What I show here are the dipole amplitudes, where the black dots are the data points. The green and yellow bands correspond to the 1 and 2 sigma bands. The dashed line corresponds to the isotropic expectation value if you just take into account the statistical uncertainties, and the solid line if you take into account statistical plus systematic uncertainties. Since everything is consistent with isotropy, we can set limits to the dipole amplitude, which are this plot shown right here, are for rigidities above 200 GeVs, which is the point where we see the breaks in all the spectra. We have a limit of 3 per mil and a measured dipole amplitude of 1.2 per mil. So this is regarding the protons. If we go to heliums, the procedure is similar. What I show here as an example is the map of events for helium, where you have a total of 124 million events, and this is the reference map, which is the exposure. And again, we need to compute the efficiencies in order to correct our exposure time maps, so we don't have spurious effects. What I show here is the most relevant efficiency for helium as a function of the magnetic latitude. And as you can see, the drops at high latitudes are 1 order of magnitude lower than in protons. This means that the acceptance that we were using for protons, which was a reduced acceptance or full span, the particle needs to go through all the layers of the AMS. Now it can be extended to a layer 1 acceptance, where the events in the layer 1 does not need to hit it. So as I show here, this increases our acceptance and our number of events. So if we follow the same scheme as I explained before, we can compute the dipole anisotropy. And what I show here is the dipole amplitude, where again the data points are the black dots, and the green and yellow bands correspond to the 1 and 2 sigmas, and the 2 dash and solid lines to the isotropic expectation values with the statistical and the statistical plus systematic errors. Again, everything is consistent with isotropy, so we set limits to the dipole amplitudes. And in this case, for 200 GeVs, we have a limit of 3 per mil for helium and a dipole amplitude of 1.7 per mil. Last but not least, we can also measure the carbon and oxygen anisotropy. The analysis is very similar, and also they are consistent with isotropy. So I directly show here the plots, and for rigidities above 200 GeVs, we have a limit for carbon of 1.41%, and for oxygen, a limit of 1.73%. So this brings me to my conclusions. The AMS measurements have shown new features in the proton and light primary nuclei fluxes that challenge the traditional models. In this sense, the study of the directionality of the cosmic rays provides additional information to the rigidity dependence of the fluxes, and in particular, it may help to understand the origin of the previous observations. In this particular presentation, like a measurement of the anisotropy in the rival directions of proton, helium, carbon, and oxygen in galactic coordinates has been performed. And since everything is consistent with isotropy, we set limits to the dipole amplitude, and these are the values for proton 3 per mil, for helium 3 per mil, for carbon 1.4%, and for oxygen 1.73%. And that's all. Thank you for it.